In this video, we are going to talk about internal energy. So we'll start with the definition of internal energy, and then we'll use that to explain the intricacies of it. So internal energy is the sum of the kinetic energies and the potential energies of all of the particles in a system or of a substance. So we can write that in shorthand. Internal energy is kinetic and potential. Obviously, we are remembering that it's actually the kinetic energy of all of the particles and the potential energy of all of the particles. We do not care about the large scale, the macro scale properties. If I throw a tennis ball across the room, we don't care about its overall velocity. We are looking at the individual particles and what they are doing. So we need to obviously understand what we mean by kinetic and potential. Kinetic is really straightforward. This is related to the speed that the particles are moving. So that's really easy for us to then understand if we look at three states of matter. In a solid, the particles are vibrating back and forwards about an equilibrium position. They do have kinetic energy, but they don't have huge amounts. In a liquid, they are free to move past each other and around the container, so they do have more kinetic energy. And in a gas, they are moving on average with a really high speed or really high velocity. They have a lot of kinetic energy. The other thing that we can relate kinetic energy to is temperature. So if we take a solid and we heat it up, it will vibrate more or with more energy. If we heat a liquid up, the particles will move around faster. If we heat a gas up, the particles will move around faster. So within the same state of matter, we can change the kinetic energy by heating up the particles, making them move faster on average. What do we mean by potential energy? Potential energy is due to the state or due to the position of particles. So it's probably a lot easier if I use some more common examples. We're quite happy with the idea of gravitational potential energy. Gravitational potential energy is equal to mass times gravity times height. So if I have an object on the floor, it has very low GPE because its height is very low. If I raise it up a little bit, now it has some height, it has more GPE. And if I raise it up even higher, then it has a lot of height, so it has a lot of gravitational potential energy. But what exactly do I mean by this? Well, I mean that it has the potential to fall. It has the ability to fall. If I let go of this object, it would fall down towards the ground because it has this store of potential energy that could transfer into something else. So if I relate this to my diagram of the different states, the solid particles are they're quite close together. So in terms of their ability to move closer together, they can't. They're basically as close as they can be. A liquid, they are pretty much, touching. They are very close together, just like a solid, but they are free to move past each other. So, this one over here could end up moving all the way over here. And because of that, we can think of it as having a bit more potential energy. It does have the ability to move around more. And then the gas is really obvious. We can see here that there's a large distance on average between the particles. They have a long distance that they could move to become closer to each other. So again, they have a higher potential energy. Now, you might not be that happy with my definition of potential energy for liquids. So let's look at another way of thinking about this. So here I've got a temperature graph against, time. So down here we've got solid, here we've got a liquid, here we've got a gas, here it's melting or freezing, here it is boiling or condensing. So we tend to say that solids have the lowest potential energy. We say that gases have the highest and liquids are somewhere in between. So we can relate this to kinetic and potential. Like I said, kinetic is related to temperature. So if I increase the temperature, I'm increasing the kinetic energy. So during this portion here, I am increasing the temperature, therefore the kinetic energy is increasing. During this portion here, I am also increasing the temperature, increasing the kinetic energy. What about during this bit here and this bit here? Well, during this bit, we have a state change. And during this bit, we also have a state change. So what is going on here? Well, what I'm doing is I'm putting in energy, and when I put in energy, I am breaking bonds. And this is also helpful to think of for us to think of what potential energy is. So put in energy and break bonds. So although I'm not increasing the temperature as I melt a solid to a liquid, or as I boil a liquid into a gas, I am putting in energy in order to break these bonds. These, are fixed in position because they have bonds with their closest neighbors, but these ones are free to move. And they're only free to move because I've put in energy to break the bonds. And that is also what we can think of as potential energy. I've put it into breaking the bonds. The same with liquid to gas. I've had to break all of these bonds to make the particles completely free to move. So that energy that I've put in goes into the potential energy. It could be stuck in a bond. The energy could be in the bond, but it's not. I've freed the particles, broken the bond. So hopefully you can understand that we've got two ways to think of potential energy. It's either due to the state and therefore basically due to the energy that's going to breaking the bonds, or it's in the position, using this as an analogy. One other interesting question. If I think about the energy required to melt it and compare it to the energy needed to boil it, which is greater and why? Well, hopefully you know, or you can see based on the length of these lines, that the energy required to boil is much greater than the energy needed to melt. And the reason for that is, think about the difference between going from solids to liquids. Actually, in terms of position, there is not much difference. Yes, they're free to move. Yes, they do have more potential energy, but they're quite similar. They're still quite close together. Whereas to go from a liquid to a gas, I'm completely breaking these bonds. I'm completely separating these particles. So much so that even if these particles come close to each other, they will not bond. They will just bounce off each other because they have so much energy to overcome these bonds. So it takes far more energy to go from a liquid to a gas than it does to go from a solid to a liquid. Now, in order to check that you understand this, I have a few questions for you to answer. So for each of these, pause the video and try the question. This is a basic definition. B is the answer. 4 questions now. So question 1, which has more internal energy? It is 1 kilogram of water. They are at the same temperature, so they have the same kinetic energy, but water has more potential energy. Question 2, neither. They are at the same temperature, which means they have the same kinetic energy and therefore they move at the same speed. So they are both at 100 degrees Celsius, although I've actually have made a little bit of a typo here. Question 3, it is a swimming pool. So you might think that the hot tea has more energy because it is hotter, but we have to remember that the internal energy is the sum of all of the energy of all of the particles, and there are far more particles in a swimming pool. So even though an individual particle has less energy, the sum of all of them together is greater. And question number 4, the answer is on the screen. Okay, next set of questions, pause the video and try these questions now. So we can increase the internal energy by heating or changing state or by sublimating. In each of these cases, we are adding energy. If we are heating, that means adding energy, supplying energy to the system, which could cause the temperature to rise, or it could cause the state to change. If we're changing the state, we're obviously breaking bonds, which is increasing the internal energy, the potential energy. And if we're sublimating, we are going from a solid all the way to a gas, which means obviously we have to put in energy to break those bonds. Solids have the least potential energy because of what I've explained in the previous parts of the video. And kinetic energy is directly related to the temperature of the particles and therefore the speed of the particles. Okay, one more question, a bit harder this time. Pause the video now and try this question. So this catches a lot of people out. We only care about the motion of the particles. We do not care about the macroscopic properties, the motion of the aeroplane as a whole. So we can ignore the first and the third set of energies here. We only need to care about the motion of the air molecules, which means we need to add up 30 and minus 3 and get 27 megajoules.